Hi there. Behind me is a WebGL object that I created using p5.js. It's kind of a three-dimensional landscape made of these planes, these squares, and then the squares are rotating along the X, Y, and Z or something like that. And they're moving up and down in this volume, this depth that's the canvas now. If you're used to working with p5.js in just X and Y, like 2 dimensions, and you get that third dimension by scaling things, that's kind of what WebGL is going to be doing, but it's doing them in like real life. So in X and Y and scaling to get the dimension, you're not really taking account of your angles of perspective. So nothing is really rotating around a center point in all 3 dimensions. It's kind of a fake way of making 3D. WebGL lets you do the 3D. You're doing all of the calculations, so it's kind of like a real volume that you're working with, because you're actually rotating things, and objects get shorter as they go toward the vanishing point, and the vanishing point can go off of the screen, and you can get all kinds of really cool stuff to happen is the point of this. So this is a very basic way to examine this 3-dimensional space. By using Perlin noise, we can see these movements and see these patterns, and we can get kind of a grasp of how things are laid out in the 3-dimensional volume, and then how we can get things to be in certain places. So I hope you'll follow along with this video. It may sound a little bit complicated, but it's actually a pretty easy program. I'm going to go through it line by line and explain to you the basics of using WebGL. Here's the program that we're going to do. I'm going to include a link to this program in the description to this video. It'll be fully annotated just as you see it here. I'm also going to go through and type this program out with you line by line and explain what's going on, and then maybe do a few things, make some adjustments so that we can see the output a little bit differently, and then just set you loose to enjoy this code and do what you want with it. We're going to start with the new sketch in p5.js, and we need to change the create canvas to say we want to use the 3rd dimension. So normally we just have the X and Y, and we indicate what the parameters of the X and Y are with some value, and we can use the available window width and height with this command. You guys are familiar with that. What about the window depth? Now this would seem really intuitive to put, and if you thought this, then congratulations, you're pretty smart. But programming isn't always smart or intuitive. It just is. So we're going to tell p5.js that we want to use that 3rd dimension by indicating that we're going to access it using the WebGL library. So anything that goes in the X parameter here is going to be calculated using the separate library of tools. And that's what we're going to do. Now, this is essentially, it's an infinite depth. Like, it can go off in infinity behind us and infinity in front of us. The center point, the origin of our volume, is going to be 0, 0, 0, and that's going to be halfway in the middle of the screen along the vertical and horizontal axis. It's also going to be halfway from the viewer to the far depth, and that's kind of a weird thing to wrap our head around, because we don't have a depth in our screen. It's a flat, it's a flat screen. There's no depth there. We have to imagine that there's a depth there, and p5.js is going to make that depth in numbers, but it's still being represented on a 2-dimensional screen. So ultimately, all those 3-dimensional values have to be kind of arranged in a 2-dimensional output that goes to the viewer wherever you're at, wherever you're looking at this volume from. This is where if you're going to have a camera that moves around your volume, that's where this comes into play, because you can change the origin, and that's going to make things move around the viewer. And if there's no frame of reference, then it's going to look like the viewer's moving around the objects. That's kind of something to remember. When we start looking at the walls of our volume, so if in 2D if you go off the edge of the screen, you might want to handle that in a certain way. So if it's like x is less than 0, then we're going to make x equal the width. So we'll go from the left to the right hand side. Well, how does that work with depth? If we don't have a window depth to work with, where's the 0? Where is the depth, the end of that? We have to define that. So we're always going to have to constrain the depth according to some arbitrary amount. And I usually set it to the height. So the depth will be the same as the height of the screen. And that kind of creates this cube environment. Even if the x is a little bit wider, that accounts for your field of view. Like if you were looking out of your eyes, you have kind of a wider range along the x than you do along the y. So it gives it a more of a realistic feel in terms of viewing a three-dimensional space. So after all of that, explaining a little bit of the WebGL complexities, we're going to go up to our global space, and we need one variable, and it's going to hold an object. So we're telling p5.js, take particle and put an object into it. And then we can access the object's variables and the object's methods using this variable. Now it's just declared. I need to assign it. So we're going to take that variable and we're going to set it equal to, and we're going to use the new declaration. So we're telling p5.js this is going to be a class or a function, and we're going to assign that complexity to a single variable. So now this particle has all the complexities of a function or a class, and we can use that in various ways. We're going to shut off the stroke because in order to rotate three-dimensional geometries, we need angles. So we have to take that geometry and figure out what is that geometry in terms of angles. And then we can start adding and subtracting and rotating angles to get our perspectives in 3D. So one of the things that you'll do is you'll take an object and you'll subdivide it into triangles. And triangles have 3 angles that all add up to a set amount. And then you can use those rules for triangles to figure out how to rotate a geometry and make it look like it's in its proper perspective. So all geometries in WebGL are made of triangles. And if we add a stroke to those geometries, the segments between the vertices will be lined. So then we'll see all the triangles that make up that geometry. And that might be cool for some kind of output. But if you just want the raw output and you don't want the subgeometries, the triangles, then take the stroke off. And that's what we're going to do here. In Draw, we're not availed to the alpha, so we can't use transparency and opacity tricks in our output. We can shut the background off in Draw and leave the trails, the accumulated output, but we can't have what it's doing in that frame be a certain intensity and then it mixes with whatever output is there to create some other new thing. We can't do that. At least I don't know how to do that. If you do, leave a comment. So for now, we're going to set the background to, I'm going to say 50, because some of our output is going to be black and I want that to show up. So we're going to use a really dark gray. p5.js assumes that our origin is in 2 dimensions. 0, 0 is the top left hand of the screen. In WebGL, we have 3 dimensions, and that origin is in the center of the volume. So you can imagine a cube is our screen, and the 0, 0, 0, or the very starting position, is at the center of that cube. That being said, if we have a set width of 100, then the left-hand side is going to be -50, and the right-hand side is going to be 50. So we have to do that calculation. We have to divide our entire dimension by 2 and then take that value, make it negative for the top or the left and positive for the bottom or the right. And for the z dimension, positive is toward the viewer and negative is away from the viewer. The first thing we want to do is rotate our object. So we're assumed that we're at the origin of this volume. So if we rotate the global volume, it's like moving the viewer. So we're getting a different perspective of what's inside this volume. When I print this output, it's vertical, so it's like a flat wall facing the viewer. I want it to look like a ground plane. So one of the things we can do is rotate the x-axis, or rotate along the horizontal, and it's going to turn away from us. So I'm going to take pi and multiply it times a fraction, 25%, and rotate the x that angle. And it's going to pitch it down so that it looks like a ground plane. And then we can kind of see the patterns a little bit better. You can play around with this to get a different perspective, and you can also use different axes. Notice here I didn't just use the keyword rotate. I added to the end of it a capital X. You can do a capital Y or a capital Z. And when you do, you're specifically telling WebGL to rotate that volume, whether it's isolated to that subshape or the whole volume itself. We were going to move it along that named axis. So here it's moving along the X. If I put rotate Y, it'd move along the vertical. Z, it would be rotated like spinning, like traditional rotating. Once we have it rotated to be a ground plane, we need to give it a material. Because it's 3 dimensions, it can have different reflectivity. What's reflecting the light we can see, and what's not reflecting the light is in shadow, we can't see. So we're working with light, right? Light needs to reflect off of things, and depending on what it is, it gets reflected off in different ways. Like a mirror is going to reflect something different than, like, say, a piece of fabric. It's going to be more reflected or more diffuse. There's also a type of material in WebGL that lets you just test things. So you're not sure what material you're using, you're not sure what light you're using. You just want to see this geometry and be able to use it for testing. That's called normal material. We're going to use it. You can change these materials afterwards if you want. A normal material, because it will assign the X, Y, and Z reflections to a color map, we don't have to give it color parameters. So this is empty. If we used ambient material, so this is going to reflect light, and it's going to reflect it based on whatever color the object is. And if we want it to be, that object to be white, then we need to specify that. Ambient material wants color parameters because it's going to use those color parameters to tell p5.js what color light is being reflected off of this object. For now we're using normal material because it processes faster, and we get in a whole range of colors depending on how we look at it. So we're going to get red, green, and blue just looking at it statically. But if we start rotating it around in the volume, we're going to get different color patterns based on what angles are being reflected to us. Are we getting more Z angle? Are we getting more Y? Are we getting more X angle? If we are, we need those colors associated with those angles. Once we have our normal material and we've rotated it, we're going to call the function update. So particle has an object associated with it. That object has inside of it a method called update that's going to do some stuff. So we use a variable, the dot syntax, and then we call it using update. So now we need to make our function. This is where it gets a little bit extra. We called that function particles. It may contain some consistency. So when I first made this program, I had a certain thing in mind, and I was using the positions X, Y, and Z to do some of that stuff. And then I changed how I was doing it because I liked something else better, and I never did change those variables back. So even though these variables are named for positions of the object, they're not really the position of the object. So let's just keep that in mind. I hate to confuse you like that, but this may happen in programming where you change things, how they perform, and you don't change the variables, so they may not be properly named now. It's just a fact of life. So I'm going to use this variable as an array. I'm going to do this for the x, y, and z because I want to keep track of attributes for each one of those dimensions. So let's just copy that a few times, change the x to a y, change that x to a z. Now we have an array that will hold an x, y, and z modifier, we'll call it. And since I'm not using an x, y, and z that's like a variable, instead I'm going to go through two loops. I'm going to loop through the columns and I'm going to loop through the rows. And whatever return is of that loop, that's going to be my x and y. So the column return is going to be my x, the row return is going to be my y, and then inside that double loop, that's where the action is going to happen. And I have my location already just from the loops. So then if I want to do anything to that object at that location, then I can start applying those variables. And I need those in an array because I want each one of those objects in the grid to have its own set of variables or adjusters. To do that, this array won't have an index value. Normally I would use the array as the index value, like for I equals 0 to the length of this array. But I'm not doing that in this case. I'm looping through the rows and columns, and the multiple of those actions is going to be the index value or the quantity of this array. So I'm going to start out with a quantity of 0. This should actually be index. Matter of fact, I'm going to change that to index because that's just going to make life so much easier. I don't know why I had quantity to begin with. I think it's because I had it set up a little bit differently. So the index value starts out at 0. When we go through our double loop, we're just going to increment that index value, and then we know how many of these objects we have, and then we can use that in our to tell it which element we're on. Once we have that index value, now I need some offsets because we're using Perlin noise to describe not only the rotations, which gives us the color of these objects, but also the height. So it's going to be kind of undulating and moving in these waves. To do that, we need the offsets. So I need a z offset. This is in a three-dimensional noise function, this is our last parameter. And I need that parameter to be unique for each object, and I need it to be retained because I want to add to it or subtract to it so that I can get relational noise on the z value. The x and the y don't need to be arrayed because they're going to be cleared inside the loops, because I want the z noise to be relational to the y and I want the y noise to be relational to the x. I want the x to be reset at the beginning of both loops. I want the y to be reset inside the first loop, and then I want the z to change inside the second loop so that we're getting this noise where the increments are kind of compartmentalized. So I'm getting an x, I'm getting, like, say x is a, then all the noise to that would be AA, AB, AC, AD, AE. Then you go through the loop again, you reset it, and now x is B, and the noise associated would be BA, BC, BD, like that, and so on and so forth. So you're getting this kind of like subs of subs of subs. For me, it was hard to understand in terms of language. I get it visually, but explaining it, even to myself, is kind of difficult. So forgive me, please, if I wasn't able to explain it as thoroughly. But if you go to the example page and you look at the two-dimensional noise function, you'll see that the x offset is outside of the loop and the y offset is inside the loop. And the x offset gets reset, whereas the y doesn't until it goes back to a certain place, and then it is. So that's what we're doing here, but we're doing it 3 times. So there's 3 nested orders of this movement through the loop. We need a size for our grid, an x size and a y size. How many parts are there? Is it 5 by 5, 10 by 10? To do that, we're just going to use a global variable. We're going to set it to x, and we're just going to divide the width by a number. Now this is a square grid, so it's really not critical to have 2 separate variables, because it's a square, you could just use one. But if you wanted it to be a rectangular grid, then you'll need two variables, and that's why I have two here. So just incidentally, they're the same, so it doesn't matter. But if you want to change it, there you go. You have both of those variables to work with. Now we have our offsets, we have our arrays declared. We can make two loops to create the initial conditions for our grid. Okay, so we need our first loop, which is going to be the columns. I don't want the output to go off of the edges of the screen. I want it to be nice and kind of inside the viewing area. So to do that, I'm going to start out on the left side, 1/4 from center, and I'm going to go to the right side, 1/4 of center. And then I'm going to move, print one object, and then move so far, and then print the next object, move so far, print the next object. And this is so far that I'm moving, increment x. So inside the for next loop, we need another, that was old school, wasn't it? For next. That's like 1980s, right? Okay, so inside the for loop, we need another for loop that handles the rows. And we're going to increment that one by the y. So we have the columns being incremented by the x, we have the rows being incremented by the y. Clean this up a little so I can see what's happening. So we're inside both loops now. The first thing we're going to do is assign to the position, which really isn't the position. This is just going to be a modifier for our position. We're going to do that for the x, y, and z. So we're just pushing using our dot push syntax to push zeros into every one of the elements of the arrays for the pos x, pos y, and pos z. We have our z offset array that we need to push a value into for each one of those elements, and we're going to have them all starting out on the same value. Now we're at the end of both of those loops right here. Our variables have been created. Our initial state is there. Now we're ready to update and do whatever we need to do. So this isn't going to happen until we call it in draw. But we're going to create a method that we're going to use in draw called this.update. And it's going to use all these variables we just made to do stuff. Inside the method this.update, we need to start the quantity, which isn't quantity anymore, it's index. I changed it to index. We want to change our index, we want to set it to -1. Each time update runs, it's going to start out with an index of -1. Then inside the loop, we're going to increment that index value so that the first index value is going to be 0, and the next one will be 1, and it's going to go all the way through the end to the number of elements in this array, or in these arrays. Real important part here, set our x offset to 0. So now we're going to start with the same Perlin noise for x, and then anywhere else down the line, y and z, we're going to offset it a little bit, and then that's going to give us our 3-dimensional and 2-dimensional Perlin noise. After we've got those initial conditions set, we're going to go through our loop just like we did before. A quarter on one side to a quarter on the other side. Increment the columns by the x incrementer. And before we make our next loop, we have to do a few things. We want to increment our x offset that we just cleared up there. Now we're ready to move through the same noise values, but they'll be offset a little bit on the x and y, or I mean on the y and the z. So to offset them a little bit on the y, we need to restart that. We'll restart that y. So we're getting the same x values, we're getting the same y values, slightly the same. Once we've reset our y to 0, and we've incremented our x at this point, then we're going to do another loop for our rows. Now we're in our row loop. We need to move our Y offset, just like we did up there with our X. Now we're going to do that with our Y. We need to move through our index value so that we're using the right elements in the array. Now we can set our Z offset, increment our Z offset now that we have our index value. And a smaller value. There we go. I don't want it to move too crazy. You can adjust this value to get different styles of output for your noise movements. We're going to use a local variable. We're going to call it ZN for Z noise. We're going to get the return of the map of the return of noise, and we're going to use our X, Y, and Z offsets. So this X off, this Y off, and this Z off, and that one is an array, so we have to add the index value, which is now this dot index. Okay, the return of the noise will be a value between 0 and 1, and we want to map that to negative height, comma height. So we're going to be moving toward the viewer or away from the viewer. And since we've rotated it to a ground view, ground plane view, it's going to be up toward the sky or down toward the ground. We're going to use 2 pushes and 2 pops because we need to retranslate, do a little bit of retranslating just to get the output to be a little bit different. This isn't necessary, but I like the way that it generates the output this way, and that's why I've included it. So we're going to use push and pop. We're going to translate to the column position, the row position, and we're going to offset the global location a little bit. So we're moving the Z toward us by 20%. So it's a little bit closer to the viewer. If I rotate that shape down into a ground plane, the way that I'm printing it, it's going to be kind of back toward the wall. So I want to slide it toward the viewer a little bit so that it's closer. It's just a minor adjustment. You can play around with that and get some different output. I'm going to use a global variable, local variable I call size. The size really doesn't describe what this variable does. It did do this at one point, but basically this is controlling the height, and I didn't want to use height. So we're going to map the Z position we're going to modify that Z position with the local variable ZN. This value is 0. If I wanted to add sine waves and stuff like that to it, that's where this becomes handy. But right now it's not really doing anything, but I have it in there just in case. The important value that we're really concerned with is Zn. And Zn can be a value from negative height to height. So if we're mapping that to something, that's our constraint for the object of our mapping. And then I want to set that range to something a little bit smaller. So I'm actually just constraining this output. I could do it with the constrain variable, but a constrain function. I like it doing it this way, and I can mess it around with it and do lots of different stuff. We need a local variable called rotate, or rot, short for rotate. And we're going to use the size local variable up there, which can be a value from 25 to height times 0.25. And we're going to, whatever that is, we're going to make it equal some rotation in a circle from negative pi to pi. So now we've got our objects moving up and down. We've got our objects rotating in their positions. We're ready to perform that output. And we need to isolate it, because if we don't, everything's going to move. We just want each sub-object to move on its own. So we're going to use push and pop, and now we're going to translate to that sub-object's position. Or no, we're translated there already, but it's adjusted. Now we're adjusting that by the size variable, how that's changed, and it's going to make it move a little bit in a strange way. And let's rotate those. When we rotate it, we're getting different angles of X, Y, and Z, and those angles are related to a color map. So we're actually just getting different colors for our shape as they're being rotated. I'm just doing the X and the Y. I'm not going to do the Z. You can do the Z if you want, and we'll just put that in there just in case you want to do that. I like the output for just the X and the Y. Everything's translated, rotated, we're ready to draw our shape. I'm drawing a plane because it's fast and I can put lots of these objects in the system and it's not going to slow things down too much. I don't know. You think it's going to work? Let's see. I did it again. When I was testing this out earlier and I put particle instead of particles. And I have no output. That's interesting. All right, bear with me here. If you guys know what I did, leave a comment while I try and figure this out. Okay, so 0 to height times, oh, okay, right here. That's the center of the X, so that's right here. Height times 25 is way down in hell, so let's use a fraction of that. All right, did you guys guess this was the problem? Did you take a guess that 25 times the height is way down in the basement? All right, well, if you did, you're way ahead of me and you could have been playing with this 10 minutes ago. There's our output. It seems to be working now. All right, what do you think of that? That's pretty cool, huh? So let's do a couple things, and I'll show you what I was talking about in a little bit more detail, and then you'll know how to play around with these. Let's eliminate this rotation along the X and see what the output looks like. See how it's a wall now facing us, and you can see how it's been dropped down some. So if I go down here to this first translation inside a method of our function, you can see how it's height times 0.2. Let's do that times a negative and see what happens, and just do a quarter. So now it's moved away from us. See, that's on the Z. Rows, that's the Y. Let's multiply this times 5, 0.5, so half of it. And let's set this back to the positive, and let's take off this 5 here. So you can see it went down even further. Let's hit a negative there. And now it's come up. It's come up some. And you see what I did there? Now every line, every row is printed, it's translated to the same location, every line. So it's printing every row over top of every other row. Same here. If I take that out, you can see now we just have one column. Let's rotate the Z. This is going to rotate the Z of the sub-objects. And you can see they're kind of spinning as they're rotating. And that's a neat effect if you like it. Let's turn the object back down the way that it was so that we can see it a little bit better. Let me know what you think about this in the comments below. It tells the algorithm to share this video with people like you that may enjoy it as well. So that will help out. And also, I love hearing from you guys, and share your work if you want to. I would really like to see what you're able to do with this, if you do anything with it. I guess that's it. Hit the bell, hit subscribe if you want to see more videos like this. And I guess until next time, as always, take care.